All right, last one before lunch. So we're back to the same group of people as the first talk. These slides were assembled by Stefan, so I'd like to give him a shout out for that. So in this presentation, we're going to talk about a different way about thinking about properties in SYCL. So in SYCL 2020, a lot of classes have optional properties lists that they can take. They can define a bunch of different runtime properties. And the gist of this talk is we think if we have a slightly different one that enables you to also define compile time properties, that can be useful for a bunch of things. Yeah. So like I was just saying, SYCL 2020 has this class called a property list. And this is used in many of the different class objects that exist in SYCL. So one example of this would be the queue class. Defines a property that states that the queue is going to be an in-order queue instead of an out-of-order queue. So if you want to make an in-order queue, you just instantiate a queue class and pass the appropriate property in this property list. Yeah. And so you have these properties, they're in the classes. The classes, you can query them to say, do you contain this property? But they're all runtime things. So they're all, yeah. So there's certain limits to what you can actually do with them. So in this case, you can ask your queue, hey, are you in order or not? And that's something that will work. But if you wanted to kind of evaluate these types of things at compile time, that's not supported. So C++ added this notion of kind of const expr if, which is a compile time evaluated condition, which can be a nice way to do all kinds of cool things in C++. But the current SYCL property mechanism, since it's runtime only, you can't use it in combination with these things. So that lets us introduce a new way of expressing property lists. So rather than the SYCL property list class, we have an extension that defines a new class, properties. And these new property lists can contain two types of properties. We have the existing runtime properties that contain a specific value associated runtime. But now we can also define compile time constant properties, which have values that are evaluated at compile time. And in order to use these things effectively, we're also going to ensure that all properties have both kind of a value and a key type, which is really mostly useful for the compile time variant. For the runtime variant, basically the key and the value are essentially the same thing. So I'm saying a lot of abstract things. Let's show some code. So here we're going to define a hypothetical runtime property called foo that just contains a float member variable x. So we just make a struct foo, it takes an x, it has an x, and then we just say we're going to make a key type that just is our class. Very simple, nothing complicated. But we can also use this now to define compile time properties. So in this case, we're going to define a compile time constant property bar, and it's going to take an int template argument and have a kind of const expr member variable y. So we have some slightly more complicated C++ here, but rest assured, it all works and it's all great. And yeah, so here we define a key that has a slightly different thing than our previous one did. Yeah. So I've shown a lot of complicated C++ so far. Let's try to get to the point. So we've defined our runtime property foo, our compile time property bar. We can build property lists of these things to combine them together, like we do here. And then we can use these things now in constant expr things as well. So since we're going all the way with C++ on this, because these things tend to be often very complicated template things, you may think you need to start adding complicated template types everywhere, but we try to take good advantage of C++17 deduction guides. So luckily, you can just say properties and all the actual template types of everything get automatically kind of deduced from the properties in the property list. Yeah. So, why are we doing this? Why is this actually useful? So we use our keys for our queries and for accessing. Yeah. But the useful thing here is that we're able to start doing cooler things. So we can start checking if combinations of properties or values of properties are actually valid at compile time rather than runtime. So if the user writes something wrong, we can tell them when they compile their code, not when they run it, which if you're an application developer is very useful. You don't want your users who are running your application to get some weird error when they're trying to run on the big machine. Yeah. So in the previous example, we built a property list that had our properties foo and bar and tried to use them. And since they were there, everything worked fine. In this case, we built a property list that doesn't have those things. And then we try to ask, do you contain a foo or a bar? And we don't. So in this case, actually, this code will completely fail to compile and give you some extra, type checking and safety that we didn't have before. So this is all very theoretical. How can this also be practically useful? And one way this can be practically useful is not necessarily if you're a user of SYCL, but very useful if you're an implementer of SYCL. So one of the things in SYCL 2020 is various C++ attributes as a way to give compile time information. And that can include things like required subgroup sizes, required workgroup sizes, kind of minimum workgroup sizes, things like that. And these things are encoded as C++ attributes, which are kind of the double bracket things you occasionally see in some examples. And the thing about attributes is you can't define them in a library. You can't really use them in a library. In order to do anything with them, you really need compiler support. And if you want to add a new one, you have to go learn how to make changes to Clang to add a new attribute, which is kind of a pain in the butt. So it would be nice if we had a way to define compile time properties and attributes without having to change Clang every time you want to add a new one. And that's really one of the motivating factors behind this. We've now defined one generic mechanism that you can programmatically define new things without having to modify your compiler every time. Yeah, so this is kind of one of the pieces of secret sauce here. So I can show some examples of what I was just describing. So we've defined several extensions in DP++ that take advantage of this. So in this case, we have a kernel properties extension that defines a bunch of these new properties to represent several things that previously we had to represent using these attributes. So like one of the things I mentioned was required subgroup size. So previously, if you wanted to launch a kernel and say that it needs to have subgroups of size 16, it would look something like this, which is okay. And, you have to be a slightly above average C++ person to kind of be able to read this and know what it means. But again, it requires that compiler support to be able to work efficiently. So we think something like this can be replaced with one of these new properties that's a little more programmatic and easier to read. So in this case, we just define a new subgroup size property, and you can pass that as an argument to your parallel 4. And now the compiler has the information it needs in order to compile it the exact same way. So in the previous example, I showed how you can use these things with Lambda functions, but of course, they can be useful also with functors as well, because one of our talks yesterday described how all their SYCL kernels get rewritten as functor types. Yeah, so in the previous example as well, the property was associated with specific kernel launch. So if you wanted to do that potentially for all your kernel launches, you potentially needed to pass the property to every call to parallel 4, which sometimes you may want to do, sometimes you may not. But if you're using functors, you can also just encode the properties in the functor type itself. So you do that by just defining a new getter, basically, that takes this properties tag and just returns the property list of all the properties you want to associate with that functor type. And then every time you submit that functor type, it also submits those properties with it. So that lets you define things like a required subgroup size for a particular kernel that gets automatically applied to every launch of that kernel, which often is actually what you want. This can be useful for many things as well. So we have even more extensions to do all kinds of other stuff. In particular, in this case, we have an extension for kernel arguments and annotated arguments and pointers. So one of the weirder parts of C and C++ is pointer aliasing. It's one thing the Fortran people love to say they do better. And C has the notion of restrict, kind of sometimes in the language, sometimes a language extension, and it sometimes works, it doesn't always work well. And C++, you can kind of use it in your code sometimes, but the spec itself doesn't really have a notion of restrict that is well defined. But we want to be able to use these things in SYCL, so we need a way to express it. And we had a previous attribute that could say all the arguments to this kernel you can treat as restrict. But this is another area where we can use this new properties mechanism to try to do that in a slightly nicer way. So here we declare a restrict property that has the kind of the classical notion that says any pointer or whatever pointer I associate with this isn't going to be potentially aliased. This is the only guy that's going to point to that memory. And then once we have our restrict property, we can associate it with a pointer by making an annotated argument. So on the second line, we make our kind of restrict arg that directly maps this property to that specific pointer. And then when that annotated argument gets captured in a kernel, it propagates that restrict information into the kernel, letting the compiler emit more efficient code. So another example of things you can do with this is prefetching. So we have another extension that's built on top of this notion of compile time properties to add the ability to prefetch memory into specific levels of the cache. And traditionally, a lot of people think of prefetching really as like a runtime thing that happens during the execution of your code. But it can have compile time implications in that if you need to prefetch into a specific level of cache, often that affects the instruction you actually need to emit in the compiler to do that. So we can use our compile time properties to basically add information to our prefetch operations to say, okay, we're going to prefetch this pointer and it's going to be, this amount of memory, but we want you to put it into L1 specifically. Yeah. And in this prefetch extension, we have all kinds of things defined. And some of these can get a little long because of C++. So we also define kind of shorthand aliases for a lot of these things, which we found to be a fairly common pattern when using these just because of C++. Okay. Yet another example of this is our extension for adding kind of device scope global variables to SYCL. So in this case, we want to associate a property with a device global that says the host also needs to be able to read and write this. Yeah. So yeah, it's a fairly simple idea that we found to actually be very useful that lets us do a lot of other things as well. Essentially, we're provided a generic mechanism as a way to define all kinds of arbitrary things that you may want to communicate to your compiler. And we are able to do this in a way where we just defined one thing that lets us programmatically define all these changes without having to go and modify Clang every time to add a new attribute, which we find to be incredibly useful. So here's a list of a bunch of the ways we've been using it that I mentioned, and there's a whole lot more as well. You can do things like use this as a way to give information about the kind of register amount of registers you want available to your kernel. There's a whole list of things that are FPGA specific that I won't get into. So I encourage people to go check this out and, let us know other useful things that, you think really need to be encoded at compile time. Yeah, so that's that. Thank you. And I won't keep everyone from lunch.
So James, this proposal there'd be two different things. One is compile time properties, and property lists would remain to handle runtime properties.
Well, we'd actually kind of like to replace property lists with this because this new list supports either runtime or compile time.
Okay, so you are supporting both?
Yeah.
Okay.
And you can have property lists that like mix and match. You can have some compile time properties, some runtime properties in your property list.
So when you showed how to replace attributes with property lists, you showed how to use this functor to basically attach the property list to the kernel in the same way that currently an attribute is attached to the kernel. Like, doesn't this indicate that for the attribute use case, what you'd actually want is to communicate the property list via a wrapper type? I mean, to me, it seems like this is actually what you're trying to emulate, and then you also would need to have this get member function as part of the API that then, so I think it could be more intuitive if you just had a wrapper type that takes the property list and the kernel and then gives you that information.
Potentially, yeah. I mean, this is just the first way we did
Right.
it. There may be others.
Also to point out, like with the annotation that you had, we already have a similar feature in our generic JIT compiler where you can basically also with a kind of a wrapper type annotate kernel arguments. So I think this is a good way forward.
Hi, James. So when you mention replacing our current property list with properties, well, this would miss the opportunity, or you would no longer be able to build different property lists at runtime. Do you know if users are using it right now? Because I may be naive, but
No, you can. That still works.
Oh, really?
Yeah.
But arbitrarily with different. Okay, cool, perfect.
Yep, that was a key design point.
Thank you.